Today, we're taking you on a fascinating journey to one of the universe's most mysterious and exciting places, black holes. Thanks to a new visualization created by NASA's supercomputers, we can now experience what it's like to fall into the event horizon, the point of no return of a black hole. The mastermind behind this breathtaking visualization is Jeremy Schnittman, an astrophysicist at NASA's Goddard Space Flight Center. Schnittman says, people often wonder what happens when you fall into a black hole. Simulating these hard-to-imagine processes helps me connect the mathematics of relativity to real-world consequences in the universe. So he simulated two different scenarios. One where a camera, standing in for a daring astronaut, just misses the event horizon and slingshots back out, and another where it crosses the boundary, sealing its fate. To create these visualizations, Schnittman teamed up with fellow scientist Brian Powell at NASA's Climate Simulation Center. Using the Discover supercomputer, the project generated about 10 terabytes of data, roughly half the estimated text content of the Library of Congress, and took about 5 days, running on just 0.3% of Discover's 129,000 processors. The same feat would take over a decade on a typical laptop. The destination is a supermassive black hole with 4.3 million times the mass of our Sun, similar to the monster at the center of our Milky Way galaxy. In this visualization, labels highlight many fascinating features produced by the effects of general relativity. The simulation tracks a camera as it approaches, briefly orbits, and then crosses the event horizon, the point of no return, of a monster black hole similar to the one at the center of our galaxy. Schnittman explains, if you have the choice, you want to fall into a supermassive black hole. Stellar mass black holes, which contain up to about 30 solar masses, have much smaller event horizons and stronger tidal forces, which can tear apart approaching objects before they reach the horizon. This happens because the gravitational pull on the end of an object nearer to the black hole is much stronger than that on the other end. Falling objects stretch out like noodles, a process astrophysicists call spaghettification. The simulated black hole's event horizon spans about 16 million miles, 25 million kilometers, or about 17% of the distance from Earth to the Sun. A flat, swirling cloud of hot, glowing gas called an accretion disk surrounds it, serving as a visual reference during the fall. Glowing structures called photon rings, which form closer to the black hole from light that has orbited it one or more times, also serve as visual cues. A backdrop of the starry sky as seen from Earth completes the scene as the camera approaches the black hole, reaching speeds ever closer to that of light. The glow from the accretion disk and background stars becomes amplified, much like the sound of an oncoming race car rises in pitch. Their light appears brighter and whiter when looking in the direction of travel. The journey begins with the camera nearly 400 million miles, 640 million kilometers away from the black hole, which quickly fills the view. Along the way, the black hole's disk, photon rings, and the night sky become increasingly distorted, forming multiple images as their light traverses the increasingly warped space-time. In real time, the camera takes about 3 hours to fall to the event horizon, executing almost 2 complete 30-minute orbits along the way. But to anyone observing from afar, it would never quite get there. As space-time becomes ever more distorted closer to the horizon, the image of the camera would slow and then seem to freeze just shy of it. This is why astronomers originally referred to black holes as frozen stars. At the event horizon, even space-time itself flows inward at the speed of light, the cosmic speed limit. Once inside both the camera and the space-time, it's moving in rushed toward the black hole's center, a one-dimensional point called a singularity, where the laws of physics as we know them cease to operate. Once the camera crosses the horizon, its destruction by spaghettification is just 12.8 seconds away, Schnittman says. From there, it's only 79,500 miles, 128,000 kilometers to the singularity. This final leg of the voyage is over in the blink of an eye. In the alternative scenario, the camera orbits close to the event horizon, but never crosses over and escapes to safety. If an astronaut flew a spacecraft on this 6-hour round trip while her colleagues on a mothership remained far from the black hole, she'd return 36 minutes younger than her colleague. That's because time passes more slowly near a strong gravitational source and when moving near the speed of light. This situation can be even more extreme, Schnittman noted. If the black hole were rapidly rotating, like the one shown in the 2014 movie Interstellar, she would return many years younger than her shipmates. Don't forget to subscribe for more exciting science and space content. We'll continue exploring the mysteries of black holes together. See you in the next video.